I think this computer has microphone, speaker, we'll just have to do a sound check.
Okay, if not, I think the laptop does.
Okay.
I got basically the same laptop.
Yeah, and you don't have to have the webcam going, but there it is.
Okay.
And, the Bamboo, once the Bamboo's in and running, it's just, I always use Windows Journal. And then, so, chapter 4.3.
I gotta see if I have Windows Journal online.
I'm pretty sure it's standard.
Okay.
Yeah.
And just the Bamboo, as long as that Bamboo's plugged in, you have Bamboo Dock, it'll run on that.
Yeah, we'll need to make sure we've got the software loaded on that.
Yeah.
So, okay.
If not, I can run it off the laptop.
Yeah,
as
I think
well.
so. I think so.
Okay.
Yeah. Thanks. All right. So I'm going to get into courses. So last lecture we went through. I hope I made clear the distinction between units and dimensions. We reviewed that the dimensions that we're primarily working with, that we worked in up to now, are length, mass, and time. And depending on how you combine those three fundamental dimensions, you're going to get force, you're going to get work, you're going to get energy, you're going to get power. And then from there, we name those different dimensions. And you can even think of power as its own dimension. Just like you think of time being a separate dimension in space. It's just that power is a combination of dimensions in the same way that a molecule is a combination of atoms or whatever, however you think about it. But hopefully I made it clear that there's different dimensions. The nice thing about this chapter, though, working in energy, is that everything's in the same dimensions, in dimensions of energy. Let's do another really quick review on what we covered, because this chapter really is our big physics section, if you will. There was potential energy, if you remember, that was mgh, so m being mass, g being gravity, h being height. Each one has the proper dimensions to get to energy. We covered that last time. You can review your notes. This is an example of kinetic energy. We looked at the density of air. Anybody remember what the density of air is, approximately? It's pretty easy to remember. It's about a kilogram per cubic meter. Water is about 1,000 kilograms per cubic meter, and that's why for a long time there was some controversy over whether or not air had mass or not, I guess. But so air is 1,000 times less dense than water. There are, approximately, for every given volume, only one air molecule in a given volume for where you might find 1,000 water molecules, for example. Talked a little bit about pump storage. This is turning the kinetic energy from the water flowing into potential energy. We talked a little bit about the Gordon Butte project that's going in here in Montana so that we can have more secure renewable energy, if you will. And a lot of times we talk about energy security, our strategic fossil fuel reserves, but in this case you're sort of looking at it as a strategic gravitational energy reserve, if you will. So I think we'll start to see a lot more of that. Here's an example of a lake in Scotland. And then after that we went into heat. This was Francis Bacon, who is really a big forward-thinking guy in science. We talked a little bit about James Joule and the fact that Kelvin called him out for being not crazy, like everyone else in the room thought he was, claiming that heat itself is a form of energy. And if I'm not mistaken, we went over the heat equation, but let me just reiterate that. Quick little side note. So heat equation. We've got heat, which is sometimes denoted as Q. So you might write it like this: energy sub H for heat equals Q equals this thing, C sub P times the mass times the delta T. So I'm just going to write a little side note here that this is, it's actually 4.4. This is 4.3 heat. And we can even make a nice little segue from heat into electrical, and just remind me to do that as soon as I finish this little deal up here. So obviously, this is mass, just like we talked about last week with gravitational potential energy being mgh. This is the same mass. You'd have a mass of water, a mass of air, a mass of whatever substance you're talking about. This delta T here is just the change in temperature. So if a substance is getting hotter, you're putting energy into it. If it's getting colder, it's giving energy back. And then this guy, so change in temp. And then this guy right here is the heat capacity. So just looking at this whole equation, and let's just look at this little chunk of it. How many variables do I have? Yeah, I got 3 on the right-hand side, and I got 1 on the left-hand side. So I have a total of 4 variables, and typically we're going to treat these 3 as the independent variables, sort of the inputs. And the thing on the left-hand side is the output. It's the thing we don't know. Let's do one quick little example, then we'll get into electrical. So the heat capacity for water, let's just write that down, C sub P for H2O, and it's given right here in the book, 4,200 joules per kilogram per Kelvin.
4,200, which?
Joules, as in James Joule,
Per
kilogram per Kelvin. Now, I'm going to write that this also equals 4,200 joules per kilogram per degree Celsius. And the reason you can get away with that is that you're always looking at a change in temperature. And the one degree Kelvin, one change of 1 degree Kelvin is the same as 1 change of 1 degree Celsius. So those are interchangeable. Doesn't matter which one you use. So C sub P, heat capacity for water, is 4,200 joules per kilogram per Kelvin. So looking at this equation right away, you can see, oh, it's that C sub P that ties everything together. Because I know I'm going to have a certain number of kilograms of water. That's why it's sitting down here in the denominator. And I'm going to have a certain delta T, some change in temperature. That's why that's down in the denominator. Multiply it out, and out pops energy. So let's just do the little deal in the book here. I realize I skipped over this on Tuesday, so let's go ahead and do it. Small off-peak hot electric, and this is where the electric's going to come in very shortly. Electric hot water cylinder, figure 4.7, holds 140 liters of water. So the volume equals 140 liters. And temperature initial equals 10 degrees Celsius, 10 degrees C. And the final temperature, TF, equals 60 degrees C. How do I find delta T? What's delta T going to equal in this case? What do I write to find delta T?
TF minus TI.
Perfect. Delta T equals TF minus TI equals 60 minus 10 equals 50 degrees C. Okay, now, looking back, someone said there were 3 variables. How many do I know so far of those 3? Yeah, I got 2 of them. I got the change in temperature knocked out, and I've got the heat capacity knocked out. Back to the word problems, the sleuthing that Tim was talking about. What don't I know yet, and how do I find it?
Delta T.
I don't know the mass. Oh, we just found delta T. It's right here, 50 degrees C. I don't know the mass. I do know the volume, though. So how do I get the mass from the volume? Remember the relationship there? Mass equals something times volume. No, not temperature.
Weight or something.
It's related to weight, but it's not weight, no. It's not, and it's not something we think about regularly. It does have something to do, though, with the fact, my initial statement about the mass of air versus of water. I think I might have actually used the word earlier in the lecture.
Volume times density.
There we go, it's density, yeah. So we're looking at, so mass equals density times volume. So in the case of water, I mentioned that, or sorry, in the case of air, I mentioned that water has a density of 1 kilogram per cubic meter. Water has a density of 1 kilogram per liter, or 1 metric ton per cubic meter. So we can use that straight away. So the mass, so I'm going to, so this is 1 kilogram per liter, and I know that my volume is, it's given up here somewhere, 140 liters. Pick your favorite symbol for liter. I can see I was a little on the fence there. I used a big L, there I used a little L. I'll just stick with a big L, fine. And then the volume, we know, is 140 liters, so the mass is 140 kilograms. Okay, so now we know the specific heat, we know the change in temperature, we know the mass, we have one equation and only one unknown, and that's the energy. So now we can just, as they say, plug and chug. So Q equals 4,200. I'm gonna go ahead and keep really close track of my units. Joules per kilogram per degree C times your mass, which was 140 kilograms, times your change in temperature, which was 50 degrees C. Somebody give me a number there. I'll work it myself. 4,200 times 140. Okay, we're looking at, I'm calling that 29 megajoules. Does that sound about right? I think that's what the book has. 29.4 megajoules. All right. Is that a lot of energy? Little energy? How long would it take a person, say, pedaling a bicycle to heat that water? Based on like our lectures from the first couple of days of class. If you're going to use human power to heat that water tank, how long is it going to take you? What's one human daily metabolic unit? I promised I'd ask this every lecture. It's lecture 8 and I'm asking again. So should be an easy number to remember.
2,500.
2,500 calories. Yep, there you go. It's 2,500 kilocalories. That's straight from the back of the cereal box. And so one of the very first energy conversions we did in the whole class was converting calories to joules, or calories to megajoules. Should be there in your notes.
Depending on your conversions, how big you are, that's also about 1.1 kilograms of coal, equivalent for megajoules.
And this will come easier, but I mean, I do want you to know this number. I really do. I mean, anytime I ask you, what one human daily energy is in megajoules, I really need you to know it. So either do the conversion from 2,500 kilocalories or look it up or whatever it takes, but I do need you to know this one.
4.19 joules.
Yeah, I think that's your conversion, 4.19 joules per little calorie.
So that was about 10.4.
Yeah, 10 megajoules, exactly. So, if one human energy allowance is 10 megajoules, how long does it take you to heat this water?
2 days.
Well,
Almost 3 days.
almost 3 days. And I think you saw some of that in summary 1 too, when I was comparing, somebody trying to pedal a bicycle and keep up with a car. Like, how many human powers it would take to run a car. So when you see this number, it's got to mean something to you. 29 meg. And later in the course, we'll turn this into dollars and cents and all that. But for now, I don't want just 30 megajoules to blow right past you. I want you to appreciate how much energy that is. Okay, so now let's move on to electrical energy. In this box, it was stated that this was an electrical heater, and I'd like to figure out how one might turn electrical energy into thermal energy. I think we probably also remember when we were talking about primary energy that all 500 exajoules of energy that flow through our technologies does turn into heat. And this is a particular case where that's actually the end goal, right? Making toast in the morning, taking a shower, et cetera, et cetera. When we get further down the road into 214 and whatnot, you'll start to be able to compare, an electrical heater versus a gas heater versus the solar thermal that the team made there at SpawnCon, et cetera, et cetera. So these numbers are fundamental to everything you'll ever do in renewable energy technology. Your solar plexus and all the other companies around town are doing this as their bread and butter. So we're right exactly where we need to be in terms of understanding these guys. Okay, so let's go on to electrical power. I just wanted to make sure we covered that thermal power. It's extraordinarily important as well. So up to now, we've defined energy like so. And again, what are the dimensions of energy? How do we combine mass, length, and time? There's definitely a mass in there. Should be in your notes from Tuesday. MGH is one, yeah, MGH is potential energy, but I want to get this just in terms of mass, length, and time.
Mass times length over time.
Close, that's actually momentum. Just got to tweak that a little bit to get energy.
Oh, mass times length squared over time squared.
There you go, yeah. And one easy way to remember that is just that kinetic energy is 1/2 mv squared, and this little portion right here is essentially velocity squared. Velocity is distance per time, miles per hour, meters per second, what have you. So those are the dimensions of energy that we've discussed so far. Now, when we get to electrical energy, it's a little more subtle. There are ways to go back and derive the fundamental units of energy and turn them back into mass, length, and time. for the purposes of this course, it's not important, but the easiest way to get at it is to start here, just say that power equals volts times amps. So I think you'll have a pretty good sense of what volts are. You know, most circuits are 110 volts. I think you have a pretty good sense of what amps are. It's just more or less a count of how quickly electrons are flowing through a circuit. Another way to think about it, another way to think about this guy is in terms of, and I'll write it this way. If we go back to a mechanical analogy, if we had a waterfall, something like this, we know that the potential energy at the top, again, well, let's write it this way, mg h. This chunk right here, this mg, is more or less the force pushing the water down or pulling the water down, if you will. H, the height, is obviously how far it's falling from. Every single energy system is always set up in this way. In the case of power, you can think of voltage as sort of the height. It's the potential. It's how far it can fall. And you'll want to think of M and G more or less as the current. And we're talking about electrical current now, but you can also look at it in terms of water current. Every single energy system is the same way. It's always going to have some force and then something moving. In the case of electrical, this is analogous, and I'll just sort of put a little wave there. This is analogous to force, and this one is analogous really to velocity or movement. Okay, so this is probably pretty confusing right now. Go back and watch the tape, but it all does get tied together. You just got to keep thinking about it. Yeah.
Think of how much water is flowing over the waterfall?
How much water, and in fact, that's really what this guy is. It's how much mass it is. The thicker the waterfall, the more power it has. Okay, so getting back to electrical energy. So again, this is just fundamentally what energy is. It's mass times length squared over time squared. This guy is just electrical, and we've all used the words volts, we've all used the word amps, we know what voltage is, we know what current is. Now, how am I going to get from, and I'll just put a little E here for electrical power, how am I going to get from electrical power to electrical energy? And we've actually done this problem already. When we did the light bulb problem, remember with Tim, 10 cents a kilowatt hour, et cetera, we've kind of already done this. This should be, in a sense, a little bit of review for you. So if I want to know my energy electrical, and I know my electrical power, what do I do to my electrical power to figure that out? What's the relationship between energy and power? I remember I popped quiz John it 2 or 3 weeks ago, and we didn't get it right, but hopefully by now. And again, this is even more important than that 10 megajoules, knowing the relationship between energy and power. There's one variable missing from that equation. It's time. Where does it go?
E equals power times time.
There you go, yeah. Now, what I want to do next is, so right there, we've defined electrical power by volts times amps. We've got our fundamental energy equation right there, that energy equals power times time. And let me draw a little picture. This may or may not help, we'll see. But I've got time here, and I'm just going to say this is midnight, there's O dark 30, here's noon, and here's midnight again. So let's see, right in here is 6 a.m., and right here is 6 p.m. And this is just going to be what your house energy looks like. So cruising along, middle of the night, maybe the fridge comes on for a little bit, turns back off. I don't know what else might be running it, like maybe the AC comes on for a little bit. I don't know, maybe somebody trips a night light. You got these little blurbs. Okay, then 6 a.m. comes along, you know, all the appliances come on, pumps, et cetera, then you leave the house. Everybody comes back home, get something like this, maybe you get the TV on later, whatever. All of this stuff under the curve is energy. And to add it all up, really all I did was multiply it by time. So you can see that as I'm moving along, I've just got these little chunks of time, and out pops energy. Where's power in this figure? Yeah, one way to think of it is the line itself. So if we can see that power, another way to write the equation is power equals energy divided by time. So it's more or less the slope of that line. You could also think that if you chop this guy out and just took one little snapshot, the house is consuming energy more quickly. So the height of that curve kind of represents the power too. The taller that curve, the more power is flowing into the house. But you're also right. If this guy curves up really quickly, you can also think of that as power. Okay, so that's a graphical representation between energy, power, and time. Okay, now to complete the analogy, we're going to combine heat with electricity kind of in one fell swoop. We started out talking about heat, we just went through electricity. The other equation that I know you're learning in 105 is that V equals IR. And I also know, I've already written it, I'll just rewrite it, P equals VI. The only thing I have left to do is to go in and figure out how to calculate power if I know the resistance. So there's a couple different ways to do that. I've already solved for V, so I can say P equals IR times I, right? Because that V right there just became I, equals I squared R. And that's typically how the power of heat is measured. It shouldn't be that surprising. What's that? Well, it's just electrical resistance measured in ohms. What's that? It's just current flowing through a circuit. Now, what happens, for example, in your breaker box if all the appliances are on at once? You plug too much stuff into one power strip. It pops. What pops it? What makes it pop? Too many amps. But how does a circuit really know what amps are? It's almost invariably going to be heat. There's some metal in there, gets hot, expands, bends, and flips the switch. So right there, you can see that amps and resistance turn into heat. And this is sort of, you can also think of that as thermal power. Earlier I wrote that Q was typically the symbol for heat. I can see now, just to pull all these together, I can see this is going to be heat over time. So that's thermal power. If you got a big fat resistor, a whole bunch of current going through your toaster, it's going to get hot. what, now, and so this leads to the next question, why is copper used in most wires?
So it's a big conductor.
It's got a very low resistance and it doesn't get hot. So you can either design things on purpose to get hot, like your toaster oven, or design things that don't get hot, like your copper wires. Okay, so we'll take a little break there. 30 minutes, not bad.